Hello, pre-calculus students. I'm sorry I couldn't be with you today, but if you look up on the wall, you might be able to see my face and just think that I'm there with you, talking you through this lesson. I'm going to be walking you through the first objective for lesson 1-1 on functions. It's kind of our introductory lesson here, so we kind of have to lay some of the groundwork for and some tools that we're going to have to use for the rest of at least this chapter, if not for the rest of the book. So today we're just going to be covering Objective 1, and we're going to describe a couple of ways to write down subsets of real numbers. We're going to see some ways that we are going to designate the values or the numbers that we're going to be using in various problems, especially with graphs of functions. In your study notebook, there is a place for you to write down the two objectives. And for the very first lesson, it's on pages 3 and 4. So there's two places at the very top. It says what you'll learn, and you can write in the two objectives there. If you want to just write the first one today, that's fine. And then as you can see, there's also on page 3 a place for active vocabulary. Though all the active vocabulary that's in the study notebook is only from the second objective. So any new words for today that are in bold in this first little section, you're going to want to write down directly into your notes. I'm going to start off with a little introduction to functions before we get going, and we'll get to that lesson. It won't take us very long. So a lot of people don't understand what a function is. It's kind of a weird word that we see in math, but it's kind of like it replaces the concept of y equals x. You see the notation there, f of x is how they talk about it, and it's a way that we can write both the input to a formula or a concept and its output. So we put in a number into the function and a number comes out. We put in an x and out comes a y. We put in a domain and we get out a range. And so I got some pictures of some various things in the real world that are functions. Bottom left is something that I used to have to use my Nintendo. And then you see the water fountain parabola. And then in St. Louis you have the shape that's called a catenary, which is the same as if you took a chain and you were hanging it from the ceiling. It's just been flipped upside down. It's different than a parabola, but it's still a function. This is a function. A function kind of operates like a machine. And any machine, you always wonder, what does it do and how does it work? You look at this machine and say, what do I put into this machine? And then how does it work? And then what comes out of this machine? Well, you put in dirty clothes, and then when it operates, it cleans the clothes, and out that's what comes out of the machine. So a wash machine works like a function. Here's another one. You wonder whatever goes into it and then what comes out of it, and somewhere in between things happen to, let's say it's a number. What goes into this machine? And then what comes out? Imagine having that walking around school. So it depends on what kind of machine, and maths machines are called functions. And in this one, let's say you input the number 3, then you multiply that by 2 and add 5, and out spits 11 out the other side. So that's kind of the concept of a function. We're going to be dealing with those a lot in this chapter. That's a function. We'll see that as a representation of functions a lot. Also here you also have a set of ordered pairs, which is another way that you could write a function. Or you could write a function like this with a diagram that shows the domain, all the values that you input. The function then is the operator on those numbers, and then out comes your result, which is called the range. So that's a function, a representation of a function as well. And then you can see here's a function from a Dr. Seuss book. These things go in and then out they come with a big star on their bellies. So before we get to some actual set building using a couple of different kinds of notations, let me just give you an example of something that you might use this with. I've given you an example here of, this is just a parabola. You can see down here in the blue we have its formula. x squared minus 1x minus 6. And what I'm interested here in telling you about with both the kinds of notation would be maybe where is this function positive? Where is it above the x-axis, or where is it negative below the x-axis? We may also be worried about where the function goes, off to the left and to the right, or in the horizontal direction. That's something that's called the domain. So on the top up here in the text, I've written one of the types of notations that we're going to be using. This is the first one called set builder notation. And I've got all the components here that we'll be looking at in the textbook on page 4. So I got what the set is, set x, and then I've defined, in this case, where the function is positive, where it's above the x-axis. It's when x is greater than 2, but not equal to 2, because that's at 0, or when x is greater than 3. Now we're thinking about the x values that I plug in that makes the y values greater than 0. And then the last thing I do is I indicate which set of numbers I'm using, and this indicates that x is part of the set of real numbers, so use the letter r. And I enclose the thing in brackets. Now I could also do it with this other kind of notation that we'll look at secondly, and this is called interval notation. This is the values on which you can find the answers you're looking for. And I've written a interval notation for where the function is negative, where it's below the x-axis. So I use parentheses rather than brackets to indicate that it does not include the points -2 or 3. It's everything in between those 2 points. So there's a couple of ways of doing that, and that might be something that we want to indicate when we're talking about or we're analyzing a graph like this parabola. So if you look in your book on page 4, you'll see the box there that says key concept, and I've scribbled it down in my own notes, and you should too. We've got a couple of important things that you're going to want to have down in your notes and available to you when you take a test. And that is, first of all, on the left, kind of the Venn diagram with those nested sets. So you have the set of all real numbers, which we oftentimes use in functions. And then it's broken down into either the rationals or the irrationals. And you've got examples on the right of what kinds of things those happen to be. I showed you this the very first week of school. Inside the rationals, you have integers, or counting numbers. You've got whole numbers, which includes 0 but doesn't include any of the negative numbers. And then you have the natural numbers nested in there. The natural numbers do not include 0, but go all the way from 1 up to infinity. So that's kind of useful. You can do that in your own time, or you can hit pause on this video and get that stuff down, and then unpause it when you're ready to go again. Directly below that in my notes and in the book, we have the way that we go about writing something down in set building notation. Set building notation is always enclosed in braces, not brackets, but braces. You begin by designating the set, and maybe it's the set of all x values, or it doesn't matter. They're going to give you the letter to use there. And most of the time, if we're dealing with functions, we are going to use x because we're concerned with the domain. We're concerned with the values that we're allowed to put into the equation that produce real numbers when they come spitting out the other side, when we get our range. The next thing that we do after that is we will write down the properties of this set, and x in this case is everything that is greater than or equal to -3, or greater than or less than or equal to 16. You can kind of imagine what that picture would look like. We've done it with number lines in the pre-test thing that you did, but then you can imagine maybe a graph where we're concerned about seeing those kinds of things. And then lastly, we put comma, and we list the set again, and then we use this symbol, which means is a part of, and then we will list the letter that corresponds to the kind of set that we're working with. And a lot of times it's real numbers, but in this case it's only integers. So this would include everything. It would include -3, -2, -1, 0, and then all the integers going up to and including 16. Just as an example, you get a lot of practice today. You get 14 problems of practice plus a little bit out of your study notebook. So I encourage you to scribble this down in your notes. Don't leave class without that, or if you're at home watching this, make sure that it gets down on paper so you can use it later. Okay, you're going to want to take a minute or two and look at example 1 in your book. We'll start with the set builder notation. And you can see the 3 examples that they give there, A, B, and C, where they ask you to describe the set of numbers using set builder notation. For all these, you're just going to use the letter X and that line, and then you're going to describe what values get used, the given properties of it, and then include the set of numbers that it includes as well. So look at A, B, and C. You might want to pause and take a look at that. And then I'd like you to try the guided practice. I'm going to let the video kind of go here for 10 seconds, and then I'm going to pause it and put the right answers in there. So you're probably going to want to stop it, look at the examples, try the guided practice, and then hit play again. And up, lo and behold, will be all the answers. So here's the first one. Here's the second one. This time we're looking at real numbers because it's continuous. We don't have to stop at individual whole numbers. And then here's the third one. This is the way we write that something is a multiple of pi. N times pi. As long as n is just one of the integers. So negative, zeros, positive whole numbers. And that's how we'll get negative 1 pi, we'll get 0 pi, we'll get 8 pi, we'll get all of the multiples of pi. Now, a second kind of notation I think is kind of fun. It's really quick and fast and easy and short, and it's kind of one of these shortcut ways of saying a whole lot of things. The second kind is called interval notation. And you can see in the book where it describes that it's using inequalities. It's using these things over here that we've used for a long, long time to describe subsets of real numbers. So they're either going to use brackets or they're going to use parentheses to indicate endpoints, and whether those endpoints of an interval are included or not included. So let's say you're doing all the numbers from 0 to 10. Remember, it's like where you would fill in or leave open the circle and then either have a line segment or a ray or something like that. And this is just a really easy way of kind of getting a concept of that, where it's a function rather than just a number line. So you can see in the book that they're going to have all these different combinations of these symbols of brackets and parentheses. And here we got from the starting point to the ending point, and it doesn't include the points A and B. It's everything in between. Here it starts at A and goes up to B but doesn't include B. Here it starts just after A and it goes all the way up to and including B. And here with A and B with the brackets, you've got that it would be like the closed-in circles, a line, and then another closed-in circles, and the circles at A and B. So different combinations of the greater than, less than, the greater than or equal to, and less than or equal to symbols. This is not terribly complicated. You'll get the hang of it once you use it a few times, and it's a really nice way of getting to your answers really quickly down on your paper. So you look at the examples in example 2, and I think pretty quickly you can see you're just going to plunk the numbers in there with a comma between them, and then you have to decide whether you're going to use a bracket or you're going to use a parenthesis, and just use the symbols there for greater than, less than, equal to determine which one that you're going to use. I think you'll pick up on that pretty quickly. Now, what you're going to want to do is probably look at those 3 examples and then hit pause and try those 3 guided practices yourself. I'm going to be putting them on here up on the screen in just a minute. So count to 4, hit pause, try those problems, and then we'll give it a go again. 1, 2. So there's 2a, bracket -4, comma -1, parentheses. Second one includes everything that is equal to and above -3, so we get to use our lazy 8 or our infinity symbol, and then nothing can actually be infinity, it goes on to infinity, so there's no end point. We use the parenthesis rather than the bracket on the end of that one. And the first part of this one, we say it would start on the left and go forever that way, so we have negative infinity to -2, not including -2. And then that or symbol turns into this symbol right here. You remember that from chapter 0? And then 9 to infinity in parentheses. So anyway, you will get practice with this. This is not the most complicated thing in the world. You'll get used to this really quickly because they'll ask you to do it a whole bunch of times. Okay, what I'd like you to do now is we'll get a little bit more practice, and then you'll get to start on the homework, the first chunk of them, where you're just doing these two kinds of notations, the set building and the interval notations. So take out your study notebook and turn it to page 4, where we see a main idea. And your page will look something like this, except you'll be able to see the place to put the answers. So we're going to have you work over here where you're supposed to complete the table. They want you to practice doing it both ways, doing it with the set builder notation and with the interval notation. So this will be another place you want to pause it for as long as it takes for you to try these things, and then I'll show you the right answers here in just a few moments, or whenever you hit play again. So you can test to see if you kind of are getting the idea. Again, set builder, you're going to use the brackets and all the X stuff. Interval notation, you're going to use the same set there, but just write it in the simpler format with the brackets and the parentheses. Okay, so hit pause, think about it for a few minutes, write some stuff down, and then hit play again when you're ready to see the answers. Are you ready? You must be, because you're hearing me talk. So I'm going to scroll over and you get to see here the first few where you got the set builder notation and the interval notation. So x line, x greater than or equal to -2. X is a part of the set of z, what's that? What's z? You tell me. Yeah, okay, sure. And then the interval notation beside it. Here comes the next one. X is less than or equal to 4. We just copy that back down into here and then indicate which set it is. It's real numbers because it's continuous. But then you can't have it including -0. You have to use parentheses every time you use infinity. But going up to 4, it does include 4. For the next one, there we go. We just copy that thing down in here and indicate we're working with real numbers. Again, this time it includes -5 but doesn't include 22. And then here's the fourth one. We got the or. So when we're over here in interval notation, we have to use the union image there. Everything's parentheses on this side because there's no equal to in any of these things. And then here's the last one. All multiples of 7, we have to use the same technique that we did with the one that included pi. So n, you have to throw n in there, and n has to be then all the integers so that we can account for -14 and 0 and 21. We can account for all the possible multiples of 7. Now we can't do that with interval notation because it hops all over the place and it's an infinite number of values. So there's one case where you can do it with set builder notation, but you won't be able to do it with the interval notation. All the other ones you can write them in both ways, and I would think that most of the time interval notation is just shorter and sweeter. It requires you don't have to put the sets and all those kinds of things, so kind of nice if you can put it in that format. Okay, that's it as far as notes go and the lecture stuff. Again, if you want to go see this again, just go click on the link and it'll pop up the YouTube video, So you can watch it again if you want to and scribble it and pause and go rewind and whatnot when you get home if you struggle a little bit with the homework. But I don't think you'll have a hard time with it. We got a lot of resources there in the book for you, and um, just you'll probably get most of this done before the end of class, and we'll talk about it when we're back on Monday. Okay, we'll talk to you later.